thank you very much for coming to the talk. I've done quite a bit amount of work within the named data networking area, and it was kind of very hard to pick exactly what I'm going to be talking about. And today I will focus on so-called trust schema and to enable the secure automation, secure autonomous networking. And I'll try to get a little bit more about this in further. So to start the talk, I kind of want to give you some scary facts about today's networking, today's world. Now, first, we kind of, for the last couple of years, for several years, we actually been almost living in a dream. We're always dreaming to have a lot of smart watches, smart houses, everything smart. And we're kind of getting there. As you can see, there's a lot of devices already on the market, and we're expecting a kind of like 24 billion devices in a few years. And there's a lot of investments in this area. So the future seems to be bright, with one big exception. And that exception is security. And it's mentioned the 4 barriers, but effectively the security concerns, privacy concerns, and so forth. And to give you even more scarier fact, if you've been around on the internet for the last year, you probably noticed a few huge outages that the internet had, like GitHub and some other services that you use in everyday life was effectively shut down for a couple of hours, or some of them for a couple of days. What you may not notice that those outages happened because of the IoT devices, those baby cameras, baby monitors and cameras, your refrigerators were effectively attacking the internet. It's like a kind of a scary fact, which is what I'm trying to address in the long term. And the question is, don't we know how to solve this problem? Like there should be some fundamental principles that has been established. And actually that is true. More than 40 years ago, Salzer and Schroeder has defined a long set of principles, a long set of security principles, and I'm listing here just a few of them. And one fundamental one is economy of principle. So secure system has to be simple, otherwise it's too complex to use and not going to be simple. You have to separate privileges. One key should not sign everything, but rather be defined for every specific task. You have to check everything, every element every element in a secure system, every access has to be checked. And of course, it has to be usable by the general people. So we have these principles, and the question is, why don't we have them? We don't have them embedded in our communication infrastructure. And to give you a very high level, very brief understanding of how we communicate today, like with all those devices, with all those smart devices, we're still using very basic point-to-point conversation model. With the introduction of Internet Protocol, we actually made a huge step forward from circuit switching or telegraphs that we had before to packet switching. But we didn't change the fundamental concept of communicating between host and host. So it's we just changed how we do the business. So there's a packet. If we want to send it to the destination, we shoot that packet to destination, and in case that destination wants to reply something back, it creates another packet and it shoots that packet back. And to give you an example how things work in IoT environment, like for example, if I want to, I even cannot formulate the question yet, but if I want to send a video frame from my camera to somebody, I actually have to package this camera into the packet, specifying that it's MP4, put that packet into HTTP frame, put that HTTP into the TCP package, TCP and IP package, and shoot that to the network. Note that all this different addressing that is happening in different packets. So one aspect which is dangerous here is there was no security as part of this overall communication picture. There were just packets of many layers, and that's it. And of course, we wanted to add the security, and people have added security with the question where exactly to put it. You want to put it in between the networking stacks and kind of transport stacks, you can put even higher or even higher. So kind of semi-conclusion here at this particular point is that there are many different ways of doing business, and especially it's many different ways to enable the trust control, because you trust IP address. What does it mean? You trust the kind of maybe connection. Again, what does that implies by the trust in the connection? And to give a more specific example of a problem or the mismatch between what IT, specifically applications, want and how it's secured versus what exactly building blocks available in the network, it's just the same basic example. I want to get a video feed from my camera that I have at home. So on a high level, the only thing I want to do is kind of request that stream from the camera. But before I can actually do that, I need to connect to the camera. To connect to camera, I actually have to figure out which camera to connect to. To do that, I probably need to connect to some service, probably cloud, to figure out to get access to that mapping. Finally, I have to make a few DNS lookups to figure out where to connect to. And of course, there's also DHCP process involved to actually assign addresses around. What I haven't yet mentioned is about the security of those things. So every layer actually has to be secured. And I already mentioned that there are so many different ways of securing every level, and there's no direct connection between security of different levels. So, okay, so this is a scary part of the talk. Now we, okay, something changed here. Okay, that's the last part of the scary talk. So there is a huge mismatch between kind of IoT applications, which in most cases actually focused on the data. Like, I want to get the temperature, I want to get the video feed. Of course, I'm simplifying in my description things, but there is a big class of sensor application that doing this process. And of course, I can invert it to the control application, saying the command needs to be delivered somewhere to control some entity, some Internet of Things entity. So point here is that there is a mismatch, and the second point is there is no systematic approach to trust management. And this is where the named data networking is coming to the picture. So this is a proposed networking architecture that fundamentally changes how we communicate, how we will communicate in the future, as I believe this will be our kind of next big thing for the communication. And this communication model is kind of, as I said, fundamentally changes. Instead of just shooting packets to the destination, now we asking network to give us data. There's a simplified picture of this, but effectively there are two types of packets. One is a kind of request for the data, which specifies the name of that specific data chunk and actual data item. I'll give to that get to the security in a few other slides, but the point is the security in named data networking is built in the data packet itself, and therefore kind of the whole principle of securing the communication is built into the networking architecture. To give an idea of what name is, I just exactly the same kind of IoT application example, but just in different NDN form. Instead of packaging that video frame into multiple layers of kind of multiple independent kind of not related layers, in NDN that frame will be packaged as a data packet. And name, the hierarchically structured name, as I pointed out here, will be used to determine where this frame belongs, in terms of which network it belongs, which kind of location, if it makes sense for this application, which potential view, and any other application-specific information to describe this specific piece of data. Okay, so by this picture, what I want to emphasize is that the security is built into those data chunks. And there will be more said about those items. And, oops. kind of important point is because it's essential part of the networking infrastructure, kind of networking protocol stack, we have to have a single kind of one mechanism to do the security. There is a kind of unified way of at least enabling the trust management. And I will give a little bit more examples. Oops, too fast. This is just to give an example of the actual communication. As I said, different parts of the name of this kind of long name of this data chunk define what kind of how to retrieve that data packet. And to retrieve, we send interest, and the kind of one part of the name, for example, is alex.com. It can be used to deliver that packet to the specific network using various data structures inside the network. Yes?
So if you provide this information into your data packet,
yeah.
If I, as a hacker, actually got that, I know exactly which camera your house is on and what I can do and how to get around these cameras, right? Because I know it's what, living room, video feed, front view.
Okay, so that's a great question, which relates to the privacy of the communication. So unfortunately, this is not the topic of this talk. It is a serious problem. And with the named data networking, we need to address this issue, especially when in an environment where the security is required. And there are ways to address this, kind of hiding part of the name, kind of encrypting parts of the name, hiding behind the gateways that understand the structure, doing decryption. It's more, but kind of, let's think that the privacy is not yet important, for at least for this part of the talk. And we can discuss more, but definitely this is an important topic.
Thank you.
So when you're talking about security, are you talking about the integrity of the data?
Yeah, I should have been a little bit more specific. So until later, the talk is specifically about authenticity of the data. Okay. So it's not just integrity, like the data is haven't been modified,
where it comes from.
But rather is the provenance in authenticity. The data is actually came from the camera. Okay, I'm jumping a little bit ahead of this, but it came from the camera. The camera, I have authorized this camera, and I'm actually a legitimate person to do this authorization in the first place. Okay, let me just jump this example, but the idea is that you deliver packet to the network if you're not yet in that network, but if you happen to be already there, like you just have with the phone, just walking in your room, you're already in there. Like in living kind of in the house, use kind of same process using different part of the name, delivering this data, this interest for the data to a specific location, if it makes sense. And finally, in the room, if you have multiple cameras, you deliver that interest to either all of the cameras that are configured to do the same thing, or you can specific camera that configured to operate on the living room data. And kind of you got the data back with the important part that the data is secured, and you can always authenticate what the heck is this small piece of data is. So just a small conclusion here is that first part, the shared namespace between application and the network give a huge boost into semantical meaning of semantic match between IoT applications and network building blocks. So IoT applications just need to formulate the question correctly. And the building security into authenticity into the architecture provides essential building block for the overall security. Now I'm posing a slightly different question, which refers to authenticity, is how exactly this data packet can be validated? So yes, I already mentioned that there is a data packet, it's secured, kind of signed with the public key. But how exactly to validate? So it has a signature. And the answer, and the answer is that each data packet not just carries the signature, but also names which specific key needs to be used to verify this data packet. And the insight that we got over the years is that this is exactly the same name. So it's a name of another data packet which carries the key. And that data packet also has a key locator pointing to another key that can be retrieved. So it's kind of unlike today's IP architecture where we don't have this. I mean, we have a concept of signing okay, we don't have a concept of signing data in the TCP stream, but sometimes we have this concept of kind of when we sign emails, but we don't have this recursive notion of signed data pointing to another signed data that actually needs to verify the original data. Okay, I hope that's very simple to understand. At the same time, I can continue with this kind of, not this, but hopefully this picture. Not all signatures, of course, are valid. So some signatures really came from the camera, and some signatures are not from the camera. So for obvious reason, depending on what type of this key locator which is, or what exactly it points to, it matters whether that data packet can be valid, or even if the signature is valid, that data packet is should not be valid at all. And in this particular case, it just somebody decided to publish in my namespace, which obviously completely useless. However, there's another aspect here. Even if that data packet indeed came from in my domain, it's just some other device, like in this particular case, TV, for some reason decided to publish as a camera feed, which should not be authorized because it's something is going on. And this is where the naming structure is actually coming to the place of a security privilege separation. See? So, just to highlight what I want to do for the to separating privileges and how I will achieve it. So, in this very simple example, I just want to cameras publish data that I've cameras publish data that are published by the cameras that I configured, and I'm a legitimate person in the system. So in the simplest way, that can be accomplished with a sequence of signatures. One, defining the local trust. So for example, I, with my phone carrying around, have this private public key hidden somewhere stored. When I configure my camera, I create a new key that is signed by my key. And I give that key a specific name. Okay, I think I just messed up a little bit with the order. And finally, the camera signs the data with the camera's key, which has been endorsed by a user key, which has been endorsed by the local trust anchor. So there's always this chain of certificate leading to effectively trust anchor, which should be local, unlike what we have today with the PKI infrastructure, like where we effectively trust some random CA authorities. And to give you a little bit more specific idea on how exactly those limitations can be imposed is, so in MDN, we do that using namespace design. And I already showed the picture that the camera users and the sign-in and different things, those not exactly specific. What we want to have some meaningful application-specific limits. And what in MDN we can do is to put in the derived key, in the key that we sign, some information that limits that limits purpose of that key. So for example, you can put in some places here that it's a key only bound for the living room, only bound to the kitchen, or on some other area. You can specify that it's only for the video feed, or it's only for the temperature, it's only for some other things. You can even think more about it's only valid if it's signed by some people in my household. So it's some attributes. Or you can even go further to define what time frame this key is valid for. Okay, and this is just one of the examples how such a key can be formatted, and I will just use in this example in a further talk. So in this case, I just decided, not just decided, it's one of the designs for this namespace is to put living room and put some attribution that it's a user's key. I had in mind that this key will be stored somewhere on the user Alex entity. Like for example, it's a phone, and somehow the network in my home knows how to reach device that has a key by some means necessary. And by that, I mean some form of name-based routing or some other mechanisms. We can go further and restrict the camera key to be also for the living room, but also puts information that it's only for the front view. So for kind of in this example, I'm imagining it's a camera for the statically installed camera just serving the front view of the room. And this now, kind of, with this key, what camera can do is only publish video feed. It only can publish video feed, legitimately publish video feed if it's in the living room. And it's only can publish video feed that if it's in the living room and can publish it for the front view. Again, this is a semi-simplistic example, which I hope can be extended further kind of with more complex models. Okay, that's just another example, kind of going forward to actual video feed. So what I want to emphasize here again is that the hierarchical names that are built into the core of networking infrastructure can not only be used for networking purposes, so kind of as we do with sometimes with IP networks, IP masks. In this case, it will be like prefixes to deliver, to move the interest towards the data, but also used to define the security context. So what this data actually, or what this key, key has a power, but what this data is about and how it can be secured, which keys are actually allowed to sign this data. So as I put on the slide, it's to differentiate levels of security. But so far, what I was been talking is on a conceptual level. So yes, we can define the namespace, we can define these logical restrictions, and kind of what we need is actually a tool to not just logically define these restrictions, but other practically and formally define those restrictions. And this is work that I have been doing with my colleagues in UCLA to define so-called trust schema. There's not quite a good definition of what exactly trust schema, because it has different meaning. It's a language, a very simple, kind of formal language to define the relationship between data and key names. It's also a tool, which I'll show in a few slides later, to automate the process of for authenticity and signing. And kind of again, it's also a method to define the trust model. So it's kind of multiple definition of the same of the concept. And on a high level, it's a very straightforward thing. So it's a kind of a simple language, a formal language to define rules. Like this data packet must be matched to this data to this key and nothing else. It's a set of these tools, set of these rules. Those rules has to end up with some of the trust anchors, one or more trust anchors, or flexible. Plus, each rule is defined as a form of regular expressions. To give you an idea how this rule can be defined, let's see this very simple example that from the previous slides. So let's say there is a living room key that I want to kind of... so I have like a major key like in my environment that is very, very secret, and I do not want to expose that key like too often to do signing operations. So in this example, I want to have another key that is kind of more online, but only works on the living room. Like only can operate on devices, can configure devices, or configure devices only in living room. So to do that, I can write this type of rule in the language that we define, which just is saying that effectively exactly this name with just some simplification of what user and the key ID kind of information about key is, and it has to be signed by the trust anchor. That's fine. With exception is that not generally enough, because now in this case it's only this rule applies on the living room, but doesn't apply to a different one. So kind of we went a little bit further, and we can define a kind of a more flexible way to define the location. So now this rule applies to anything, any key. So now we can define by one rule, capture the fact that the key has if it has kitchen in there, it only works in the kitchen. If it has I don't know, first floor, it will be like only on the first floor. And I can even go even one step further and relax to some extent the prefix part, meaning that it not only works in my Alex home environment, but also can work in a different smart home. It's just a matter of defining different local prefix. So that's kind of fundamental concept of defining a set of trust schemas that works in different application contexts and that, different application contexts. And the reason I'm emphasizing here is that defining trust schema is not a simple task. Like this example is a kind of trivial example that I worked out for this presentation, which I tried to cut all the corners possible, like only focus on this living room, only focus on kind of one aspect, like not even hierarchical structure for the living room representation. But if you really want to define it in kind of more general context, that to define it, that to apply not just for the smart home, but also smart building, smart campus, then it's really non-easy task to do. And ideally, the security expert needs to define those rules, trust schema, their relationships, and those should be applied to different environments. And kind of that ability to generalize these rules is extremely important. I already mentioned kind of implicitly that the trust schema, like the way you want to limit relationship between keys, influences how application name things, as well as influenced by how application name things. So if something does not make sense for the application, then schema cannot capture that part. Or if something may make sense for the application, then it needs to be put in certain places inside the schema. To just give you a more complete picture of this is another rule for cameras. Same thing for video feed. So it's again, this data packets can only be signed by this specific key, but because they have some commonalities and prefixes. It doesn't have to be as kind of hard-coded prefix. So kind of what we have in the PKI model today. So in PKI model, the TCP connect or a TLS connection is authenticated only if you have the main name is exactly matches to the name of the key. With the trust schema, we can define kind of relatively flexible way of doing business, like a flexible way of defining relationships between names and the keys. And this is kind of a complete example. One second. I already emphasized that this schema applies to any trust, any home environment that, or any IoT applications in different home environment, and we only need to specialize this trust model with a specific trust anchor.
Quick question. Yeah. Sorry. Do you have an infrastructure for this grammar, like an editor, and a compiler, or something to validate these?
That's a great question, and this is what I was kind of trying to lead to.
Oh, sorry.
This is still so early work. Like we have tried this language, kind of implementation of this language in a few applications. So there's a library that doing interpretation for the authentication process. So we applied this language into our named data link state routing protocol. We tried in the file, kind of with the prototype of file sharing application. We tried in multi-user chat application. But again, it's still in the beginning process, because defining this trust schema is extremely not easy task. Even though you think you got it in the first place, kind of then there's some problem is happening. And this is, I hope to have a kind of more tight collaboration with kind of language people to help me do security analysis, like to provide the ability to understand, given the defined schema, does it actually do the intended behavior, or it's doing some, or allow some bizarre data packets to be constructed in the way that completely unintended. So that's a very important security question that is not yet captured. Yeah.
Do you have a formal model for this trust schema? Like, how do you know your design is fully functional, has achieved all the objectives that you want? Is there such a list of desired properties?
So not at the formal level. So for every schema, when we design a trust schema, there is a informal trust model that what we want to achieve. Like as I was showing in the slide, that there is a data feed. That data feed must be signed by the camera, and it only can be signed by the camera authorized, and I can be only authorized by the kind of legitimate person in the system. So this is not exactly a formal description. It can be put in the form of a graph, defining this relationship between entities in the system. And then trust schema needs to realize only these trust relationships. So there's actually some small project that the student is trying to pull off right now, doing this simple analysis based on this graph representation of the trust model. It's just still more work to be done to understand the full impact. And just additional point here is, right now we have very simple language. I mean, you can barely call it a language, but it's still kind of formal description. It's a question how to define it in a more general way, to define kind of policy in a more simpler way, not just kind of that relationship between prefixes, but also kind of prefixes of the prefixes and kind of combination of these prefixes, with the addition that it should not break the trust model, look at this abstract trust model. So I feel there's a lot of, even with this simple language, there's a lot of potential. Like it's already covered a huge area of trust, and we're kind of trying to explore it and apply for military environments. There's a DARPA share program that I'm currently it's only kind of in preparation stage, but they're already looking at this environment. We're working with a small startup that trying to apply a named data networking and specific named data kind of trust scheme approach to secure data from solar panels. Look at some analytics data from solar panels. This is kind of a lot of potential and a lot of questions that yet to be answered. Okay, for the sake of time, I just simplify this a bit. So the trust schema, as already mentioned, is not just a language, but also a way to automate to the whole process. This part already exists in our implementation, so it's not exactly compilation of the tools, but some form of interpretation of the configured rules. So given a data packet that has been signed, you supply it to this interpreter. It's doing the processing, fetches keys if necessary, and give you the answer back. But the same tool, the same rules, just in a slightly different way, can be used to the sign operations. So given data packet, you kind of construct this data packet, you don't know yet how to sign it. You just supply it to the kind of another interpreter that signs, and it's trying to interpret which key is supposed to sign this specific data packet. So it's non-trivial task. It's again another good research topic to figure out all the potential implications of that, but it can happen. What we have been working on is this process of endian key management, which is extremely important part of this picture, as you actually not just need to sign kind of specific data that you supply, but also you need to get the key that has been authorized for this specific purpose. I specifically put a couple of pictures here that saying that this key management is not done by a specific PKI system, by a specific CA somewhere in the cloud, but rather it's delegated to a specific namespace, specific element that you are doing the operation. I'm not going to talk more about this, but I will be happy to talk more with you later. So we defined the protocol that you can ask for certificate within this specific namespace. And that request would go to a device operating on this namespace. So for example, if I need to get certificate from user Alex, it would go to my phone, and kind of I will need to approve or disapprove that request, after which the process will repeat, and either you need to go to more certificate authorities or already got to the point. Okay, sorry. So the point of this is to emphasize that just this kind of relatively simple language can do a lot of good things to improve security for the purpose of acceptability or like usability of the system. Because if we force every user to do the verification by themselves or kind of looking at the data packet saying, okay, yes, it has to match, it's a good data packet, it doesn't match this name, it would not be usable. With the trust schema, you just run the system, assuming you trust the trust schema, and it gives you positive or negative result. To switch one more gear is kind of towards this autonomous networking. There is one insight that we got during the work in NDN is that every bag of bits can be a named data. And if it can be a named data, it can be packaged as a data packet. It can be assigned a semantically meaningful and hierarchical name, and it can be secured. And this, I already give you a few examples of what those secure bag of bits are. It's kind of the actual item of the data feed. It's a key that signs this data, key sign that key or that signs the data. But it also applies to that trust schema approach. And that's kind of important element of this picture. So the trust schema is also a bag of bits. It can be packaged. It can be distributed around the network. And that's very, very important part of this schema, of this system. Just because this trust model can be formalized and moved around, it's actually give a lot of potential for all network elements to operate independently. I give a few examples here is that the phone, if you kind of, let's say schema has been distributed around already, phone has this trust schema, it can verify every single data packet. The camera, like in the opposite way, if I send a command that's signed by me, it can do the verification of the command on its own because everything is there, like you just need to do the verification. But it's more than just that. If routers have this trust schema, they can do exactly the same operation. They can just get a data packet that they're forwarding, do the verification of that data packet. So it's kind of extremely good thing to have the shared kind of the data packet that application uses for the verification for kind of understanding what this data packet is, and the network uses exactly the same data packet, exactly the same security. It's such a interesting thing. Yeah.
Yeah, something that's running through the back of my mind. Mm-hmm. What is the overhead on this thing? Because now I think you're looking to do a lot more at the packet layer. Right? I could be wrong. I'm not a networking person, but that's my sense. I don't know if that is true or not.
So I have several answers to this question. So if you blindly apply this approach, yes, it may have more overhead. Like if you use a public key cryptography to every single data packet, yes, it will have more overhead because it's way more complex to do. Is it feasible to do that with today's technologies? Probably not. But also there are multiple ways this process can be optimized. As one thing, again, it's always have its trade-offs. So like the optimization that I just will tell has a trade-off. So you don't have to sign using public key cryptography to sign every single data packet. You can go on a larger unit. So you can sign a group of 10 packets. You can just go semantically and assign, okay, so each frame is some form of aggregated, like hashing, whatever, and then just sign once operation. But again, the trade-off, if we go with that direction, which is feasible today, is now you kind of lose an ability to verify individual data packets. It's possible to do in a group, but kind of...
But some applications might require you to do that, right? Some highly secure.
Yeah,
so,
yeah.
Okay.
But hold this for a moment. I have a kind of long-term idea how this can be solved in the future. Do you have a question?
No.
Okay. So just give one kind of almost end of the technical part. So what I've been talking about with the trust schema is about authenticity. But don't forget that authenticity and the trust management is the core part of the security. So for example, today we have, when we use the TLS connections, we're actually not relying on encryption to provide us a kind of meaningful security, but rather the trust management. So they kind of use both in both directions, but it's more important to ensure that you're talking to the bank than the fact that you just have an encrypted connection. Because if you just have encrypted connection, you just encrypt the connection, like nobody knows what exactly you're talking to. But maybe it's some hacker, I don't know, from Russia you connected to for some reason. But if you know that you connected to the bank, now you can encrypt that connection and so forth. So this is exactly what we kind of vision for NDN is there is a fundamental building block for the authenticity on top of which you can solve the access control and secrecy in several different ways. Because again, there is a trade-off in each of the ways. Because we can always solve the secrecy in the same way TLS is doing, like kind of trying to establish a form of a connection, even in the data-centric model, with where we're losing ability to do multi-point communication. We can go to another extreme and use just a form of public key encryption, then we're losing the forward secrecy, like the concept of forward secrecy. And there's always some grounds in the middle where you don't want to lose completely the kind of multi-point communication and yet keep some forward secrecy. So I'm happy to talk more about this, but let me switch gears to a concluding part. So just this is kind of concluding part is that with NDN, many of the security principles that was laid down many years ago are now becoming feasible, or at least we see that they are part of the networking infrastructure. Like for example, there is only one trust management mechanism that you need to work on. The naming structure that built-in in architecture provides you effective separation of privileges to kind of work on. Assuming every data packet is properly signed with the public cryptography, you can verify every individual data packet, like for either purposes of verification or access control. And finally, there's a lot of automation possible for this process. And to give you kind of a final takeaway about this talk is today what we have with the TCP/IP is really bad for IoT. It's first of all there's a lot of dependency on the cloud, but especially there's this mismatch, the fundamental mismatch between what application wants from the networking and security perspective and what is provided by the network. And NDN solved this. And as I mentioned in the beginning, it's the next big thing, especially in these environments. And I already mentioned the last point that the building blocks are inside the NDN. And kind of switching gears for my future work and how I see myself in here in FIU. So I have this vision of the secure named data networking of things or secure autonomous networking. So this is where I want to be. This is where we are. So let me start where we are. Right now we have a lot of cloud IoT. We have a lot of Internet of Things devices. Like I have a few at home. Some of you have Nest devices installed at home. But many of those things have a huge dependencies on the cloud, which is great until yesterday's disaster with Amazon S3. And there were multiple examples of lockdown homes, lockdown offices just because cloud for some reason not working or there's bad connectivity. What I want to get is that we want to get to the picture where we use cloud. Cloud is a great thing. For many different things, but we don't depend, have this high dependency to install a new device, to connect to the device, and so forth. But of course, there's a lot of things needs to be done in the middle, and I see three big things. So one big thing is there's a need to enable a lot of experimentation with this named data networking technology. It's a new thing. We started working for this 2000. Oh my gosh, 10. That kind of project started. But again, what we have done so far was not 100% focused on IoT. It was mostly kind of understanding the overall architecture, understanding how the wired internet can be moved forward with NDN. But to go with to actually deploy it, to actually see this named data networking deployed, this needs to go from the edges. So there has to be, I think that's my second point. Oh, no, sorry, it's a third point, but I'll mix them together. We need to experiment with actual applications. Like we try the new ways of doing business, like with the new emerging areas of applications, like vehicle networking. That's some of the elements of networking exist today, but not that interesting. And one of the work I did, preliminary work I did, was to figure out the traffic information a few cars ahead of you. So that's kind of high-level, simple questions that what is the traffic in front of me, or like at some intersection, which easily solved by using this NDN, this named data. You ask actually meaningful question. You put intersection, some information about the question, and you throw this packet to the next car. That car can throw this to the next car. But this is just one example. I feel there's way more novel application scenarios that I haven't even thought yet. And that's really, really excites me. And this is what interesting process that relates to the question of how it's feasible to do. And imagine, I don't know, 10 years, or maybe more. We have 100 billions of devices, all of them like scattered around. Not all of them actually producing data every second or every moment. Therefore, they can actually help each other. So, and if we have a system like a networking infrastructure, actually moving beyond the networking infrastructure, but rather we integrate networking, processing, storage. Look, everything works kind of seamlessly with each other. Now they can help each other. Like everybody can help. Let's say I have some power at home to deploy some small accelerator. Then that accelerator can be used by small IoT devices to do very complex public key cryptography and actually achieve the goal of signing every single data packet and verify every single data packet. So it's kind of these three big things that I feel for the future. And there are a few dimensions. I went for the vision, but now it's kind of more on a practical perspective what I've been doing and what I'm planning to do in the kind of near term and a little bit more long-term future. So I've done several works in different dimensions. As I mentioned on the slide, it's in the security direction. One of this is trust schema work. We have done work on name-based access control. So it's access control that's trying to leverage the same kind of name structure to figure out what permissions are granted, what kind of key we need to get. I've done quite a bit of work on the networking level, so kind of how, besides the implementation effort that I'm leading, but this is kind of deciding the algorithms for interest forwarding to leverage, to utilize knowledge of this stateful forwarding in NDN. And of course, there's application layer topics that I was working on, which kind of all trying to do some new stuff that not really possible. With the cloud, everything is possible, but without dependency on the cloud, now we have many, many different problems. So for the near term, I actually have a few projects that one is funded and one hopefully funded. I'm not going to jinx, but we have some. And both of these projects that I mentioned on the slide is kind of NSF, and the second one, NSF Intel. They directly aligned with the directions that I want to take. So one is building, kind of, or continuing building the core NDN infrastructure just to enable general community to try out the NDN. We do a lot of open source implementation. Our implementation is open source and free to use. We try to engage in different platforms. We did some Android work. We did implementation for very, very constrained controllers, like with 32K memory available and very slow processor. So this is this direction, and the second one is an example of tryout of NDN technology in real world, and specifically at the edges. So what we will do in this project is to try out the augmented reality application in the campus environment without having a cloud infrastructure. And specifically, focus in there is how to integrate the FPGA acceleration into this picture, given the augmented reality processing is really, really CPU intensive application. So that's two big projects that with my current collaborations. There's a few more that currently, one in pending, one in preparation. The first one is a proposal to NIH, and I just want to emphasize that, different way to say it. That proposal emphasizes that NDN is not just networking, it's not just for networking people, but rather this concept of data-centric hierarchical naming structure is actually useful in many different areas. And this one is for air pollution data collection and data sharing. So right now, in a conversation with the colleague from air pollution department, have a lot of data, and that's data, first of all, it's scattered around in different places. They have a completely unrelated naming structure. The security is probably non-existent, and they don't even know whether that data is correct or authentic in the first place. With NDN, because you would focus on securing every data piece, you add the provenance to every data piece. You can add, on top of that, a lot of analytics of specific parts of the data. And longer term that I hope I'll get support in this department and collaborations inside the department, and I think there's a few even outside department, engineering department, and I think even beyond that, is two general directions. First of all is in networking and system security, and one project that really excites me is in the future is to apply the same principles of data centricity, data-centric security to operating system. So it's not just secure the data, or secure data while it's stored, secure data while it's moved, but rather secure the process of creation of the data, secure the way the keys are generated, key privileges separated inside the process, inside the operating system. The schema that I described, so far we're thinking in relatively small number of dimensions under which we can separate privileges, can define the scope of what this key can be used for, what cannot be used for. I'm really looking forward to see beyond that and to apply more complex, multi-dimensional ways of understanding attribute-based different attributes for the scoping the work. And finally, I want to go even deeper with the IoT environment. So as I said in the beginning of the talk, today we have smart homes. But I hope with this work with the named data networking, it's not just going to go for the smart home or individual homes, but rather we're going to build the smart neighborhoods, smart streets, and smart cities, and hopefully smart country, or at least the smart states. Okay, so this is just a concluding slide that highlights a few interests in named data networking. So this is a current NSF-funded project that I'm participating in. But beyond just this and academic institutions, a lot of companies joined our NDN consortium, showing the interest, and not just showing interest that that's interest in technology, but rather Some of them even trying to apply this technology in their environments, in their applications. Okay, so thank you very much, and I hope I didn't comment on the privacy, but again, that's a huge, it's still open topic. There are a few directions that we thinking to approach, but again, it's still a complex issue.
So, given the cloud-based service environment, we design services. Of course, if you think that there is going to be a lot of problems, people getting locked out of their house. So, a lot of that issue, do you think that could be solved by better architecture design in cloud-based services rather than jumping over to the NDN?
I mean, some of the things can be addressed, but just to think about what needed in IP architecture to actually support this cloudless IoT. What you can do, you can kind of implement NDN-like elements. Look, you can forget about IP addresses going to destination instead of use a multicast, or completely forget IP. So in theory, you can do that, but the NDN already provides you this kind of unified mechanism of operating. It's there's a lot of thought put into kind of NDN, like why we do business in interest and data exchange, to ensure that there's a flow balance. There's always a kind of feedback between interest and the data packet, so you can do congestion control, because otherwise. So kind of the short question, yes, we can try to implement something kind of less cloud dependent using existing infrastructure, but it would actually look like NDN if we do so. Like it's kind of and what I'm trying to kind of pitch is we actually should use this technology that we spent like the last 7 years, or like I can calculate like the basic math right now, kind of losing me.
So, what challenges do you see for these future internet architectures to be realized actually? Because anything that is proposed to the existing internet always seem to slow. Internet develops really slow, and for future internet architectures, they actually intends to solve the problem that exists in these kind of networks, but they all kind of move sidewise. For example, you see, they all wanted to solve what the internet facing today, but then they all moved to
Okay, so great question, and I was waiting for that. I will just try to compare IPv6 versus NDN.
Yes.
I mean, we have been IPv6 for so many years, and we're still not getting there. And the kind of question to me is, why do I think NDN would actually be deployed versus or like in reasonable time frame? And my answer to this is, IPv6 doesn't bring qualitative new qualities to the network. It's still the same communication model. Effectively, the only thing that changed is number of IP addresses like available for the nodes. And that has been addressed with the NAT technology in the first place. So it's kind of not that urgent, doesn't bring any qualitative new things. So that NDN, on the other hand, is actually bringing new qualitative things. It's kind of changing the model. But I agree, it would be challenging to switch, kind of one day to switch to NDN. And therefore, kind of one of my vision items was to try the edge-in thing. I could try this emerging applications, like I mentioned IoT in this presentation, vehicle networking another one, sensor networking another one. Like when we got those many applications at the edge, and they would effectively force the ISPs to adopt the technology and force the providers to build the hardware, and effectively we will have NDN deployed. Question when? If just edges would be enough, then that would be enough. But we will have NDN deployment. That's for sure. Okay.
So the question of how you come up with trust schema, I'm not sure that's the right name, but anyway, basically you think of this as some sort of security policy which could be super complicated, and like if I have a bunch of devices in my house, you know, do I have to spend a month trying to figure this out? And I don't do it. So I got the sense that you were suggesting that maybe because of the hierarchical naming, that gives you sort of a way of having a kind of default policies which would make a lot of sense for a typical user. And so maybe the task of figuring out the trust schema would not require an enormous effort by each individual. Could you comment on that?
Again, there are two answers to this question. So one answer is simple, yes. Yes, naming structures definitely helps kind of define the structure, how to build a trust schema. And kind of one example, the key has to be shorter than the data name, so that you always have to go into the decreasing dimension. So, but again, it's not fully addressing your question. What we're not expecting is that each individual user actually coming up with the individual schemas. That's kind of one of the reasons to actually define the generalized language, where hopefully a set of experts will sit in one room and like, okay, so this is smart home. This is number of devices can exist in this network. This is typical policies that kind of make sense for this environment. Let's define this trust schema this way. And now that what user needs to do is there's a set of kind of generic policies that can exist, and user, okay, I want to use this one and instantiate this policy. So this is my expectation for the trust schema in the long run. I hope I answered.
Seems reasonable.
Yeah.
Okay, so what kind of courses you would like to teach if you become our faculty?
Sure. Kind of given my expertise in kind of this networking and the security area, so I'm really interested in both networking, network security, and I'm guessing there's a lot of courses, especially with telecommunication emphasis in FIU. So there definitely, I'm open to all networking courses, like from this basic introduction in networking, kind of higher level network security, but I'm also interested in mobile ad hoc communication, mobile networking, and beyond that, I extremely like the programming. So kind of, if you see my GitHub profile, you probably will see that's what I've done. So I really would want to teach kind of mobile programming, programming techniques. I wouldn't say I'm teaching them right now, but what I've done so far with working with a lot of students is kind of defining different frameworks for development. So we right now using the code review system for many of our code development process, which I think was extremely instrumental for kind of teaching students the right approach to kind of programming. So it's not just you give students some task and they do some coding, but rather they have to think about how to code, how to test the code, how to integrate that code in a bigger chunk of the code, and how to pass the code review process, which sometimes is extremely not easy. Okay, but that was not exactly answer to your question. So networking courses, that's my passion. My programming language is my secondary. Security, again, that was part of the first passion. And I think I'm open to many other courses related to networking, security, operating system, and how to build an operating system. Yeah.
Yeah. So again, I'm not a network specialist, but I figured you're manipulating how data packets move across the network. Anyway, your work, did you build like a virtual network on top of the existing network and did some experiments to see how fast packets pass, and if you increase the security level, what the slowdown would be, or anything like that, or that doesn't make sense?
So we have built a test bed. So like across, actually it's multi-continent testbed that running our kind of prototype forward implementation that effectively runs NDN on top of our linux on top of IP.
Right.
So this part we have done. What you're talking about, we haven't done yet.
No, but do you have any results from that? I mean, how does it stack up to maybe if you didn't have the network? You know, you say you have a multi-continent network,
Yeah.
so you're sending data. Are you comparing your data rates?
So it would not be. So our prototype implementation in no way stands against the hardware Cisco routers.
Right.
So even we do such a comparison, it wouldn't be fair.
Yeah, but at least you get an idea how good or how far you have to go.
I mean, we have some numbers, but they're not so great so far. So it's definitely slower. First of all, it's not hardware implementation, but again, there is also additional overheads, additional data structures. Talking about this overhead, we have done, there are a few other folks that has been trying to understand what is the potential of the implementation, and so far it's looking pretty good. So there's I mentioned the stateful forwarding. It's kind of each interest requires each router to store state until this interest is satisfied. And kind of analysis shows that this memory requirement is not that much bigger than today's networking requirement for TCP connection. Like when we need to do this BD, bandwidth delay product, to ensure that the full capacity is utilized. It's about the same size. It's larger, same ballpark. Processing is larger, and it's kind of one of the contention points, kind of how to exactly do efficient implementation.
All right, let's thank the speaker.